Hello everybody, my name is Professor Mikel Duke and I'm from the Institute for Sustainable Industries and Livable Cities at Victoria University in Melbourne. I really hope you're enjoying the third NICE Summit at UTS I hope you enjoy my presentation, Nitrogen Recovery from Wastewater Using Membranes. So how we might design our membrane systems takes into consideration the way in which we treat our wastewater and what we do towards a more sustainable circular economy approach. So currently we treat our wastewater from industry or from communities to meet certain discharge requirements at a cost in terms of chemicals and electricity or energy before we discharge to the environment. However, as we continue to grow, this is becoming not sustainable anymore. And so what we can do is look at recovering compounds from our wastewater in a financially viable way, as in a means to remove these compounds and pay for the cost of the equipment that does it. But obviously these systems cannot achieve a complete removal. That's at the requirement of the environmental health reasons. And so then we need to decontaminate. And in considering how we might achieve this with our complete membrane solution, by putting these two systems together, we can show that the system which recovers the resources can do this in a way that not only pays for itself, but also pays for the decontamination as well before, so that nothing of no contaminants are sent to the environment at all. I'm going to show you today work on membrane processes to recover the nitrogen in a means by which is economically viable and at the same time reduces greenhouse gas emissions. So to recover nitrogen from membranes, there's several ways to do it, and I'm going to focus on the membrane contactor or membrane distillation approach. So commercially, you can obtain the membranes from 3M called these membrane contactors called transmembrane chemisorption, which effectively use an acid stripping solution on the inside of the membrane to remove the ammonium from the wastewater. Membrane distillation is very similar to membrane contactors in that they use a similar type of membrane, which is hydrophobic, that doesn't let liquid through, but does let the ammonia, volatile ammonia through, but does this not necessarily using acid. In this case, it uses a vacuum to strip the ammonium out, a sweet gas, or in direct contact membrane distillation, it just uses a water. So when we looked at applying the membrane distillation approach to some industry wastewaters in partnership with Greater Western Water, we first took a sample from an industrial power station which had an ion exchange regeneration waste, and then we also took an aerobic digester effluent from a food waste site. When we applied the membrane distillation at the bench scale, we were able to show that you could strip the ammonium from all these wastewaters. And the interesting finding was that even the ion exchange wastewater at pH 6 showed a removal, where anything above 1 and this enrichment factor shows that you can strip it out of the wastewater. However, when we tried to replicate the results on a synthetic sample, the pH 7 ammonia and water solution showed that you don't actually strip it from the water, you instead concentrate it, where you can see the enrichment factor is below 1. When it's adjusted to pH 11, it does come out as you would expect, because now the ammonium is now an free ammonia form, and therefore it's volatile and it can be removed. However, so when you have an electrolyte in the system, so we're trying to increase the complexity to try and find out what's happening. Well, the industry samples do let it out. We thought the electrolytes might be responsible, but no. By adding sodium chloride and sodium sulfate, you then go return to concentrating. But it wasn't until we added carbonate that we found that that's where we got the similar results to the industry samples. So in the presence of carbonate, something is happening to the chemistry that allows you to strip the ammonium out of the wastewater. So to understand this, we completed a study to explain what's occurring through the chemistry of the ammonia water system coupled with carbonates. So we just essentially followed a very well-known theory in membrane processes, which is known as polarization, which occurs when something is removed from the membrane selectively. What's left behind, as you would expect, it concentrates near the surface. So in the case of membrane distillation with ammonia and carbonates present, while you're removing the water, you also remove carbon dioxide from the water in its free carbon dioxide form. And in doing so, you can create at the interface of the membrane a rise in pH from in this case, this is the ion exchange regen solution, which we use as an example, rises from pH 6 up to pH 8.5, where you can then cause the ammonium to be released. And this is occurring because as this carbon dioxide is being removed, the carbonate equilibrium shifts. In doing so, it consumes a proton, and it can take this from the ammonium molecule, leaving behind an ammonia molecule, which is free to then come through the membrane. And so this was a good explanation to what we were observing with the industry samples in the presence of carbonate, which we called pH polarization buffering. Then we moved to a pilot trial in partnership with Central Highlands Water, with funding from Intelligent Water Networks, where we then installed a pilot plant on site at Ballarat South Wastewater Treatment Plant. So the treatment plant has an activated sludge process which uses aeration, and the sludge, after it clarifies, is then digested anaerobically. The solids are then removed and sent off as biosolids, and then the filtrate is dosed with lime to remove phosphate. And normally this ammonium-rich water then is then sent to the head of the plant and becomes part of its nitrogen load. Instead, we can apply membrane distillation to extract the ammonium at this point, and therefore reduce the ammonium load to the plant. We also looked at struvite as well with a colleague, Dimith Navaratna, but I'm just going to show you now this case where we located the membrane distillation after existing lime removal. So here's the pilot plant on site in a 20-foot container next to the lime dosing facility. Here's the membrane pilot plant, which was a DuPont Memcore membrane, which has a hydrophobic polypropylene hollow fibers with an area of 27.8 square meters. And we removed the ammonium with a vacuum pump, and then pass that through some sulfuric acid to capture as ammonium sulfate. So in evaluating how the performance went, we were able to measure a 93% or greater than 93% reduction in nitrogen, which was then recovered as ammonium sulfate. And this reduction showed that you could achieve effectively discharge limits below the discharge limits of the nitrogen in that wastewater. So it worked quite well over the trial period. We were trying different modes of operation, but the key thing from this pilot trial was to demonstrate how it would compare with the existing means to remove nutrients through the aeration system or the activated sludge system. So we took the cost of the energy for the aeration blowers, which they just upgraded to more efficient systems, at 50 cents per kilogram of nitrogen removed. And when we did the evaluation of the vacuum membrane distillation system, we showed that there's a reduction in the electricity demand and therefore the cost by using this approach. This in turn had also a reduction in the greenhouse gas emissions. So in conclusion, we need a circular economy approach for energy and greenhouse gas reduction associated with the nitrogen fixation and the nutrient removal in wastewater treatment. Membrane contactors and membrane distillation can effectively recover as an ammonium salt or even just as ammonia solution. When we started looking at this a few years ago, we saw an inconsistency between the real and synthetic samples, which revealed that with the presence of carbonate, an effect we called pH polarization buffering, which effectively means that the nitrogen recovery can occur at even low acid pHs when carbonate is present, in which most wastewater samples it is. And then we're able to show via pilot trials that we can recover ammonium from an existing wastewater treatment plant operation and reduce the energy costs and greenhouse gas emissions compared to the conventional activated sludge process. So thank you very much.